Hey, today we're working on trig integrals. I have this new quiz, Trig Integrals 101, and I actually have 102 of those integrals in here, and I'm just gonna practice a bunch of them. I don't know how many I'll do. We'll just start and do as many as I feel like doing. So on the board we have this integral tan to the fourth plus tan squared. And with this integral, what I find with the integrals of tangent, what you want to do is you kind of want to build up from just tan squared. So I think what I'm going to do is before I do this, I'm just going to look at what is the integral of tan x. And that can be looked at, we can just break that down like sine x over cosine x. We could do a u substitution, u being cosine of x, du equals minus sine of x. And doing the substitution, what I'll do, I'm just going to add a negative there and a negative there so that I'm not changing the expression. And then we can rewrite this as negative du over u. And then that's just going to be integral of du, integral of 1 over u is going to be ln u. So we're going to have negative ln u. But I'll substitute back in cosine. So we'll have negative ln cosine x plus c. And then we can just use this minus sign and bring it to the exponent. Just the exponent rules for logarithm. And that's going to give us ln, should have the absolute value here. Absolute value of secant of x plus c. Okay, good. So that's our integral for tangent, first power. Let's look at tan squared now. Tan squared x dx. This is actually a pretty easy one, because what we can do is we can use this formula. Tan squared plus 1 equals secant squared. This is derived just from the from this formula. Oops. And then if you notice, if you divide through by cosine squared, you'll get this. So then using this, bringing the 1 over here, we're going to have, this is going to be the same thing as the integral of secant squared. Secant squared x minus 1 dx. And we know the integral of secant squared, because that's just the derivative of tangent is secant squared. So what we're going to have is just going to be, let me just, it's not an integral. Coming down here, we're going to have this integral is going to be tangent of x minus x plus c. So that's our tan squared. And that's going to be part of our answer up here. So we're looking for tan squared. We have our tan squared. I think what we can do, I'm trying to think if I need tan to the third. Yeah, let's do the integral of tan to the third. And then this one, see if I can remember how to do this. Yeah, let's rewrite this as tangent of x times tan squared of x dx. Should use different color just to be different. So, but then we have, using again our this formula, we can rewrite tan squared of x. So we're going to rewrite this We're going to rewrite tan squared as secant squared x minus 1 dx. We'll just distribute this. And we'll have tan x secant squared x minus tan x. Here's where you kind of start seeing where I've needed to build up is then we already know this integral because we just did it up here. Well, I've struggled with this board. Okay, right here. So we have that already. And then we know the derivative of tangent is secant squared. So what we'll do is we'll do a u-substitution here for tan x. du is going to be secant squared x. And then we're just going to have, this is going to be just u du. And then we already know that the integral of tangent is ln of secant x plus c. So this is going to be u squared over 2. But, you know, kind of, let's just rewrite that as tan squared x over 2 minus ln secant x plus c. And that's our integral of tan cubed. Then finally, wow, I'm putting a lot of work into this one little problem. I don't think I'm going to be able to do 102 of these, but we'll see how far it gets. Let's do tan to the 4th. But what you'll see with all these tan integrals, we're going to use the same trick over and over again. We're going to pull out a tan squared. So we're going to break it up this way. Is what we're looking for. With anything tan and secant, we want to use the derivatives. The derivative of tan being secant squared, the derivative of secant being secant times tan. So you generally try to pull that out, pull out the derivative, and then do a u-substitution. It's our general strategy. So then again, let's take this one and rewrite it as secant squared x minus 1. Then we'll distribute. So we have tan squared x, secant squared x dx. We'll close that integral, and then we'll do a separate integral with tan squared. We'll do a u-substitution. I'm not going to do the u-sub. We'll just kind of do it shorthand. This is going to be u squared here, and this is going to be du. And then we already know this integral over here from above. So this piece here is going to be tan to the 3rd over 3. And what was our tan squared? It's just this tan x minus x. We just need to change the sign as we get a negative there. So we're going to have minus tan x plus x plus c. Okay, so all we need to do now is we just need to get back to what was the original problem, which is integral of tan 4 and tan squared. So let's just write these together, and this is kind of the punchline. What kind of color that is? Yeah, let's use that crazy color. So, oh, I hate that. Yeah, we're not doing that. Never using that again. So, sometimes I leave out the x. I don't know. It's just I get impatient and I try to write it quickly. So, here's our tan to the 4th piece. And then we have the tan squared integral, which was this. And the thing with a lot of these integrals, what you get is you get a nice cancellation. This cancels with this cancels with this. And we're left with our final answer is going to be just tan cubed x over 3 plus c. We're done. Let's see if we got it right. That's correct. Okay, so one problem down, 101 to go. And clear the board. Okay, problem number 2. I think I like this one better. That one was a lot of work. Cosine squared of 2x dx. Okay, the important thing to know here is um, the double angle formula for sine. And what I'm going to do, what I like to do is have, while I'm working on this, a couple of cheat sheets. So we'll use the Trig cheat sheet. And then also what I want to use is just the integral cheat sheet. I mean, it's nice if you memorize these, but occasionally I want to be sure, or it's just quicker so you don't have to keep like revisiting some of the things that you already know or should know. Okay, so the double angle formula right here, cosine squared cosine squared of a equals a half 1 plus cosine 2. So let's just let me just rewrite that using this format. So this can be rewritten as, and like, if we can do like a really, I don't really want to make a U-substitution there, but like if the angle's 2x, this angle just doubles, so it becomes 4x. So we just doubled this angle. And then now we can do our quick U-substitution. Although you can do this in your head, but I don't mind writing it out really quick. So like that. And then what you can do is, actually I kind of do mind writing it out, but it's too late. I already did. I want to take it back. Yeah, all right, let's just do it. So then we have our substitution. We're going to substitute u here, and we're going to substitute our dx is going to be du over 4. Okay, so then let's just integrate here. So our integral for a half is going to be a half x. I'm kind of confusing it with my substitution. Let's just kind of break it like this. So then I don't need to use a u sub here. Okay, so anyway, we have, this is going to be a half x. And then this guy here is going to be, it's just going to end up being 1/8 sine 4x plus c. And then you can see if you just multiply this 2 and 4, you get the 1/8. The integral of cosine sine. What I'd really do if I was just doing this on my own is I would just integrate the cosine and then divide by 4 without doing the u sub. But it's up to you how you want to do that. Then, so wait, that's our final answer. Let's check that. The only thing we could do is you could try to put this back into, get the angle back to just being x, but that's up to you, and that's equivalent. Let's see. So it's gonna be this one. That's correct. Okay, so 2 problems completed. And I'm thinking if I really want to do this, since we just did something so similar. You know what I'm gonna do? We'll just do it as we went through the whole we went through the process, but let's just do something really quick. So the integral of tan 50x, I can kind of just, if you do out the pattern, you can then just kind of remember how it works. So it's going to be 1 less. So it's going to be like tan to the 4th of x over 4 minus tan squared x over x. Let's just do dot, dot, dot. And then I don't know, maybe that was that was kind of a cheap way out for me to do that. Let me just write it out. We have that, and then the integral of tan cubed. Again, you just do one less than the power here, so this is going to be tan squared of x over 2. Make that look nicer. Oh, sorry. It's interchanging. It's like the signs change for each term. Like this. And then what you see when you add these together, this cancels with this cancels with this. And we're left with our answer of tan to the 4th x. He threw this pen. It wants to work when it wants to work. And I just don't know how to fix that. But there's our answer, tan 4th x over 4. Good, so that's 3 problems down. 99 to go. Integral of cosecant squared. Just write that out. Wait, I wanted to do blue. Okay. So there's a trick to doing this one, but I don't think I want to use the trick just because I don't think anyone really likes the trick. So let's try to do it a little more systematic. What I'm going to do is we'll just write it in the form of the sines and cosines. So this is the same as 1 over sine x dx. And what I'm going to do is I'll just multiply the top and the bottom by sine x. And the pen wants to fight back. I'm just going to keep going though. So we'll multiply that through. What I'm trying to do is set up the U-substitution. Basically what you want is you always want, I mean, in a typically what you want to do is you want a substitute u in the denominator somehow and have this be your du in the numerator. Of course, it doesn't work here because derivative of sine is cosine, but what we can do, we can't easily change this to a cosine, but we can change the denominator to a cosine. So what I'll do is I'll rewrite this. We'll leave the sine in the numerator, and we'll rewrite this like that, just using this basic identity, right? And then you can just manipulate that by subtracting cosine on both sides. And then now what we can do is our u sub. I'll make u equal to cosine of x, and then therefore du is going to be minus sine of x. Yeah, let's put a minus sign there and a minus sign there, just so that this will work out nicely. And then we end up with 1 minus u squared. We already got our du. We got our minus sign up front. Okay. And then I think we can do this without partial fractions, just because I don't feel like doing the partial fractions right now. Let me see. Okay, let's do the partial fractions. So we end up, we're going to write this like this. We're going to separate this as right, because you know what I'll do is I'm going to do this out separately. I want to do it so it's clear to see. I don't want to rush that part. Let's just do our partial fractions here. So what we want to do is we want to split this into, this is going to factor right here as 1 plus u, 1 minus u. So let's actually just rewrite it that way. But then we also could see that as some constant value A, some constant value B, like this. And I think I'm not even going to use the cover up method right now. What I'm going to do is we're just going to solve this the long way. I don't know why. I just don't feel like doing the cover up right now. So what we're going to do is we'll multiply, let's multiply through by this. So if we multiply everything by that quantity, we will end up with 1 equals A 1 plus U cancels, so we're going to get A times 1 minus U plus B times 1 plus U. We'll distribute that out. I'm going to, let's just distribute through like this. Just flipping to the other side, just because I feel like it. Then what that means, we're going to say A plus B equals 1. And then negative A plus B is equal to 0, because there's no U term on this side, right? We can write it like that. So then you kind of end up with a little system of equations. And I'm just going to, well, we could add these two equations together and we get 2b equals 1, or b equals 1/2. And if b equals 1/2, then a is also going to be 1/2. So then, this is a pretty long method for doing this. We probably should have just used the trick, but I don't really like the trick. So let's go, I'll go back to the, get back to the integral now. So we're going to have, we're going to have negative 1/2 over 1 plus u minus 1/2 1 minus u. Well, this is du and this is du. Okay. And we can integrate real quick. We get minus 1/2 ln 1 plus u minus 1/2 ln 1 minus u. But actually what I forgot, there's a negative sign right there. So what we can do is when we integrate that, that's just going to come out and change that to be a plus. Okay, next what we can do, let's pull out a 1/2. And then what I'm going to do is just using the rules of logarithms, we can write this. This is a negative sign here, so this can go on the bottom. And we can write this like this. That's just using the, it's just this property. Okay, so that's just a formula that we can use to simplify. So, okay, so doing that, okay, so the next step, what I want to do is I'm going to multiply the top and bottom in here by 1 minus u. I just want to get this into a little simpler form. So we'll have 1 minus u squared. No, sorry, that's not right. 1 minus u all squared over 1 minus u squared, multiplying top and bottom by 1 minus u. And then we can use this half and bring that in as a square root. So let me just write that for you, like so. And then square root on that cancels on the top, so we're going to end up with ln 1 minus u. I'll just keep the absolute value sign for now. and our 1 minus u squared. And I think this is a good time to substitute back in our u. What was u again? I forgot. It's like a half hour ago. U is cosine x. Okay, makes sense. Good. So we'll rewrite this ln 1 minus cosine x over 1 minus cosine squared. The pen wants to work. 1 minus cosine squared x. Okay. I think actually what I could do, I'm actually trying to think how I need to make simplification work. What we should have done right here is we could have this 1 minus u, 1 plus u, 1 minus u, write it like this. This cancels, and we end up with 1 over 1 plus u. So let me just back up a step, see how this looks. Substituting in here, we get 1 over cosine x. Oh, I don't like that. It's funny. I feel like every time I do this integral, I make a sign mistake somewhere, and it totally throws me off. Let's see. No, we're close. So let's see. If I did if I did that right there and substituting cosine, we had sine squared. How does that look? Um, no, that's not right. Shoot, I think I definitely botched this somewhere. It's usually when I that's why I was struggling right here was I was like I knew when I put a negative sign there I was going to get in trouble, but I did distribute it there. So unfair. I know I distributed that, and then we got a negative out there, right? Got negative, negative, good. We do our integration, we get that to be a plus, good. This on the top, this on the bottom. Oh, wait a second. Wait. I lost the square root sign. Yes. I lost the square root sign. Okay, perfect. So, yes, we still have a square root here, and then we have a square root here. Okay, that's key. Okay, so then if we keep going, we end up with 1 minus cosine of x over sine of x. Yeah, now we got it. So then let's just, we can, this is true now, but we could just rewrite this to make it a little nicer. 1 over sine x is going to be cosecant x, and cosine over sine x is cotangent x. Put a plus c, and we're done. So that was super long. So what you do is, it's nice to do this a couple times, then you remember it, and you don't have to like work that out all the time. But yeah, let's just check that. And then also, I'll show you the trick real quick, which would be, here, let's do the trick in a different color. So you take this and you multiply it by this on top and bottom. And then what happens, let's see, so this is going to be cosecant squared. This is going to be cosecant times cotangent. And you have, if you substitute u here, you have du on the top. So then when you integrate that, you just end up with ln cosecant minus cotangent, which is this answer here. So you see how that's really easy to do. If you remember this multiplication trick, you get to the answer in like one step. Um, but it's pretty, I think the reason why people don't like it is it's like you have to know the answer first, right? If you know this is the answer here, then you just multiply that basically what's inside here. So it's like, yeah, if you already know the answer, you can pretend to do something. I don't know. It just doesn't make sense to me to do it that way, but it's way easier. So maybe it depends when how you want it. If you're on a test or something, if you're taking a test, this is way quicker and easier. So enjoy that. So next question, we did four. Okay, cotangent. This is not too bad. Integral of cotangent x dx. What I'll do here is I'll just write it in terms of cosines and sines. So this is the same thing as cosine over sine. We'll just substitute u equals sine x du. It's cosine x dx. So we end up with, this is the formulaic, right? If you can get that, you're set. It's going to be ln of u plus c, which is going to be the same thing as ln of sine of x plus c. We're done. Pick that answer. Good. So that's 5 down. I don't know how these people do 100 integrals. Like black pen, red pen. He did 100 integrals. I'm ready to fall asleep after 5, so that just tells you where I'm at. So go on to the next one. Okay, this one, it's nice. Another one, it's nice to memorize the answer, but what we'll do is we'll do it out the long way. Okay, let me rewrite that. So cosh x is the hyperbolic cosecant, and that's going to be the same thing. So the one thing you do want to know, you want to know the definitions of what those hyperbolic functions are. And again, that's going to be in here. Where is it? Where is it? Where is it? There. So here's the definitions of sinh, cosh, and tanh. And then there's some identities to go with it down here that can be useful. Actually, let's keep that up while I'm working on this. So, okay, we have the definition of cosh, hyperbolic cosine. And yeah, this is pretty easy because what we can do is we can just break this into two separate integrals. And then the integral of e to x is just e to the x. So this is super easy. And then here you can do like a very quick u sub in your head. And if you do that, it's just going to bring out a minus sign. So you end up with minus half e to the negative x. Technically that's correct, but what we want to do is we want to simplify that. So what usually you want to do is if you start, it's nice if you can, it's not required, but it's nice if you can get to look kind of like with what you started, kind of get it in the same format. So we started with the cosh. We want it would be nice to get this into the format of another trig function. And what we can do is we can rewrite this as like if we substitute, I'm not going to make this, I'm not going to make too big a deal of this, but this can be written like this. Okay, and that's the same thing as sinh, right? The top function right there, that's identical. So this is actually the same thing as sinh x plus c. We're done. Check the answer. Good. That's correct. So next question. So by the way, this same thing's going to work for the other way, sinh. The integral of cosh is sinh. The integral of sinh is cosh. So let's use that now. So we have on the board the integral of sinh cubed x cosh x dx. And then we'll just do a simple u substitution. U equals sinh of x. Du equals cosh of x. So this is basically kind of like what we just did. Is there? Oh, is that? I don't know if that's in the reverse or whatever. Yeah. Remember, we went from cosh to sinh, so we're doing the same thing here. Anyway, we redo this u substitution, and then we can just use the power rule for 4. And so that's just going to be equal to sinh 4x over 4 plus c. And I'll check it. Okay, that's 7 down. Next one. Okay, interesting. Okay, how do I want to approach this? So we have sine cubed x cosine squared x dx. And let's see, usually with a sine, cosine, you want to either use an identity or u substitution. That was the double angle formula, but I don't think that's good here. So ideally what we'd want is we want that just to be one cosine. Because if it was just cosine to the first, we would just do a u substitution. But that's not going to work. So I think what we'll do instead is use this identity. Oh no, sorry, I got another idea. Scrap that. Let's rewrite this as sine squared x cosine squared x. I'm gonna pull one sine out. I just put it over here for convenience because what we want to do, I want that to be my du. And so therefore I want u to be equal to cosine of x. Du is going to be negative sine x dx. And what I'll do is I'll put a little negative, throw a negative in there. And then the only problem I have is this right here. So what we'll do is we'll call that 1 a cosine x. Okay. So then now we have everything in terms of we have a bunch of cosines and we have our du, and now it's going to set up nicely. So I'm just going to rewrite this thing. We're going to have 1 minus u squared times u squared du. We'll distribute this. You know what I'm going to do actually? What I'm going to, when I distribute it, I'm also going to distribute this negative in here just to get rid of it. I'm just trying to prevent making a sign mistake later on. So we can rewrite this as u to the 4th minus u squared. And then integrating that, we get u to the 5th over 5 minus u to the 3rd over 3 plus c. And then we'll just substitute back, and we're going to have cos to the 5th x over 5 minus cos to the 3rd x over 3 plus c. And we're done. Let me just check it. That's just in a different order, but that's the same thing right there. Okay, good. That's 8 complete. Oh, okay. I don't know if we did something very similar. But let's do this anyway. So we have e to the x minus e to the negative x over 2. So when you do this, you could do it either way. You could do it as the trig function, or you can do it as a exponential, keep the e and do it as an exponential function. I'm going to turn this back into its equivalent as a hyperbolic sine right here at the top here. So this is just going to be sinh x dx. And then that's just going to be cosh. So it's the only oh, there's no dx there, sorry. So it's very similar to when the differentiating the regular sine and cosine. The only thing, if you like the derivative of cosine is negative sine. Let me just write this. Derivative of regular cosine is negative sine x. Derivative of sine x is cosine x. But if we do cosh x, it's just sinh x, no sine, right? There's no it's just a positive. So it's kind of easier because you don't have to remember which way the signs are going. Anyway, let's check our answer over here. That's correct. We got 9 of them. Tangent. Okay, this is a good one. So integral of tangent x dx. You know what I'm going to do? We'll just write this in terms of sinh and cosine. But then the u-sub's even easier than it is with regular cosine sine because, again, we don't have to really worry about the signs, the sign change. I don't want you to confuse the sine as in plus minus with sine as in trig function. Anyway, derivative of this is just sinh. This is going to end up being du over u, which is ln of u, plus c, which is going to be ln of cosh x plus c. We're done. It's correct. See, again, I don't know how black pen red pen did 100. It's like I'm starting to my thinking is gone downhill and I'm only at 12. So anyway, integral of secant cubed dx. And what we'll do is we'll just we'll use the integration by parts. We'll use the DI method, and we'll separate secant cubed as secant squared x. Right, because secant the first time secant squared is secant cubed. The derivative of secant is secant x tan x, and the integral of secant squared is tan x. So our first part of our answer is going to be secant times tangent. And then this piece here is an integral. So we're going to have minus the integral of secant x times tan square x. Then this integral can seem kind of tricky. What we can do, though, is rewrite tangent squared as secant squared minus 1. Okay, so then let's just rewrite this whole thing. And we'll distribute this into here. And we're going to have minus secant cubed x plus the integral secant x. This real quick, I think we did this. Well, we did cosecant earlier, but it's very similar. And this piece is actually ln of secant times tangent. And then this is our original integral. So this is the repeating case of integration by parts. So what I like to do is I like to just call this, we call our original I. Call it whatever you want, call it Y, whatever. And then if this is I as well, we can bring this to the other side. So we end up with a little equation like 2I equals secant x tangent x plus ln secant x plus tangent x plus c if you want. Divide both sides by 2. And our final answer is going to be 1/2 secant x tangent x plus 1/2 ln secant x plus tangent x plus c. We divide 2 by a constant. It's just a constant, so I'm not going to mess with that. So that's just going to be plus c. And that's our answer. Let's check that right here. And that's correct. So let's keep it unlucky. I did 13, so we'll call it good enough there. If you go in the help, I have links to these two cheat sheets, or you can get that from the main page. I'll also provide a link to this quiz. And if you want, you can do all 102. What's funny is I had no intention of having it be 100 exactly 100. I was just doing as many. What I wanted to do is I wanted to cover, um, all the trig functions, all the hyperbolic trig functions, and not including trig sub. And then we also have in here different. Surprisingly, I didn't see any of the different angle formulas. I don't think we saw that, so I should probably do another quiz on those. But just by doing that, I ended up in the last problem in here was just by chance 101. And then, but then what I noticed is there's a problem 0. So I thought by chance I was getting exactly 101 integrals, but actually because there's a 0, I got 102. But I don't know, just a coincidence. Who knows why? So that's it. I'll leave it there and I'll give you a link to this and feel free to practice the problems.